We've been talking a lot about time efficiency, but you can actually use the same notation to refer to space efficiency too. For example, let's say you needed to copy over your input string 3 times in your code for some reason. Then the space efficiency would look something like this. Space efficiency is asked less frequently in interviews, but it's definitely something you should consider because it will come up from time to time. Efficiency is perhaps the most important concept I'll teach you in this course, so make sure you understand it before moving on. Efficiency, also called complexity, is how well you're using your computer's resources to get a particular job done. You can normally think about it in terms of space and time. How long does your code take to run, and how much storage space do you need? Let's think about efficiency in terms of cutting hair. Normally, your hair would be snipped off in clumps, and you would just compare some strands you cut to a group you're about to cut to approximate where your next cut goes. However, you could cut one strand of hair at a time and compare each strand to a ruler or measuring tape to make sure the exact same amount gets cut every single time. That's ridiculous, though. It would take a crazy amount of time, and it really doesn't matter if hair is exactly precisely cut. If you could use less time to get the job done pretty well, then you're good. Often, the trade-offs for algorithm efficiency are similar. You could take a slow, methodical approach, but there's often a faster method that accomplishes the same goal by reducing repetition. Efficiency can rely heavily on your creativity and your ability to get the most done with minimal resources. But there are a lot of known tips and tricks that you'll be expected to know in a technical interview. An interviewer will expect you to know some common data structures and the efficiency of doing basic things with them, as well as some knowledge of specific, well-known algorithms. In this case, an algorithm is just a series of steps for solving a problem. One of my favorite moments in my programming career was the first time I used an algorithm to improve my code. I had a function that took hours to run on this huge data set, but after applying an algorithm, it only took seconds. Writing really efficient code can come off with another trade-off between time efficiency and space efficiency. What if your code could run in just a fraction of the time by storing temporary values in a new data structure? For that decision, you would need to weigh whether the time of the person using your code or the amount of memory needed is more important. By the end of this course, you'll have most of the tools and knowledge you need to make efficient code. When you look at 2 pieces of code, you can maybe tell which one is going to be faster and which one is going to be slower. But how do we say definitively which one is faster and which one is slower? And how do we communicate that with our coworkers and the people around us? We can describe efficiency of code with something called Big O notation. The name is odd if you're hearing it for the first time, but it turns out to be a very straightforward name. Every time you use this notation, you literally write a capital letter O, parentheses, and some algebraic expression inside the parentheses. The algebraic expression is always going to be a mathematical function of the variable n, such as some of these examples. As you can see, these all contain algebraic expressions with the letter n. The only exception is this guy right here. Yes, the number 1 still counts. It's just another way to write 0n plus 1, so this is a value we can still use. So what does the algebraic expression mean in this case? Well, n represents the length of an input to your function. Let's say you received a secret coded message from one of your friends, and a cipher that tells you which letter maps to what. You want to automatically decode the coded messages with the cipher your friend gave you, so you write some pseudocode to figure out how you can do that. You take a string input, you iterate through it and change each letter based on the cipher, and then you output a new message. This pseudocode shows you what it might actually look like. Okay, so to get a sense of the time efficiency, we're just going to count up the number of lines. Creating an output string and returning an output string each only need to happen once every time the function is run. To represent that, we can go ahead and add a 2 to our efficiency. Now, both lines inside the for loop have to get run for every letter in the input. For those, we can add a 2n. Since 2 is the number of letters in our input string, and we have 2 lines that need to get run for each one. Hopefully the way we count up lines and turn it into something in Big O notation is starting to make sense to you. Let's take a look at some examples. If our input string had 10 letters, the calculation would look something like this, and we would end up with the value 22. To get the actual efficiency, you can multiply 22 times the amount of time it takes for your computer to run 1 line of code. If the input string was 1 million, you would have to multiply 2 million times the amount of time it takes for your computer to do a computation. There you go, looks like you've got the basics down. I need to reiterate that those were just the basics. There are a lot of complications that we're going to address now. First of all, in the previous example, we should think about the for loop. Does the for loop itself count for something? In order for the loop to work, you need to do a computation each time to get the next letter in the string. Since this needs to happen 1 time for every input letter, we can just add 1 to the value before n, and now we end up with 3n plus 2. It turns out that it's actually really hard to predict how many computations this pseudocode is going to take. For example, a lower level language like C would break down the process a lot more, and it would take a lot more lines of code, but they would be doing less work in the background. The Python version of this might be about this many lines of code, but it would be doing a lot more in the background because it's a higher level language. For example, let's look at this line. This line could take a different number of computations based on the data structure the cipher is using. Maybe we store our data in a list, and we need to check each letter against our current letter to solve the code. That could be as many as 26 checks for each letter in our input string. So ultimately, our efficiency calculation might look a little more like this. Let's go back to those example input strings we talked about before. Now, if we start out with a 10-letter input string, we end up with 292 computations. If we start out with 1 million letters in our input string, we end up with 29 million steps to go through. Because of our choice of data structure, we're doing a lot more computations than we might if we chose it a little bit smarter. Later, we'll talk a little bit more about the efficiency of different types of data structures, but for now, hopefully you realize the importance of thinking about efficiency before writing code. If you noticed before, I said you'll need at least 26 checks to get through every letter of the alphabet. In reality, it's unlikely that you'll have to go through all 26 letters each time. When we're discussing efficiency, we often talk about it in terms of the worst-case scenario, where we would have to check all 26 letters each time. We focus on worst case because it puts an upper bound on the amount of time our code is going to take. You could also talk about efficiency in terms of the average case or even best case. So if we're talking about letters in the alphabet, the worst case means we would have to go through all 26 letters. However, the best case would be that we find what we're looking for on the very first try. But on average, we're going to fall somewhere in the middle, around 13. In a perfect world, iterating through a list of letters is going to take an average of 13 times. Sometimes it'll be a little more, sometimes it'll be a little less, but it's fair to say it'll be about 13. If we're going to try and calculate the average case efficiency, it's going to look a little more like this. In the end, we'll get 16n plus 2. Now let's go back to our point about approximations. If we consider the average case, the worst case, or the best case, it's all still going to result in big O of n. In an interview, you might be tempted to combine the average case, the worst case, the best case, and just give an answer like this. However, the best case, the worst case, and the average case might not always approximate this nicely, so you really should specify to your interviewer which case you're talking about. Since the amount of steps can vary widely based on the specific implementations, we normally use approximations when talking about efficiency in Big O notation. Since the efficiency of the pseudocode we wrote before could end up looking like any of these and even more, we would say that the efficiency is actually about big O of n. If you're writing code for production, you definitely care about the number of computations and want to minimize it. However, in an interview, your interviewer doesn't care that you can do that exactly, but just wants to know that you are thinking about efficiency and can calculate it if you need to. By approximating, we're really saying some number of computations must be performed for each letter in the input.